German engineers arrived in Morocco's mountains with equipment that seemed absurd. Massive mesh panels, steel frames reaching heights of 6 meters, installation crews ready to work at altitudes exceeding 2,000 meters. Their mission? Pull water directly from air in one of Earth's driest regions. Local villagers watched skeptically as these foreigners assembled what looked like giant fishing nets across mountain slopes. But within weeks, those nets began producing something that had been scarce for generations: clean, drinkable water condensing from morning fog. How does mesh transform invisible moisture into flowing water? Welcome to Macro Forge, where we explore the technology solving humanity's most critical challenges. If engineering that creates resources from nothing fascinates you, hit subscribe. Let's discover how fog becomes survival in the desert. Southern Morocco's anti-Atlas mountains face a crisis most developed nations can't comprehend. Rainfall arrives maybe twice annually. Underground aquifers that sustained communities for centuries are running dry. What little groundwater remains carries such high mineral and salt content that drinking it causes health problems rather than solving them. The statistics tell a brutal story. 60% of residents have no running water infrastructure. Daily survival means women and children walking multiple kilometers across dangerous rocky terrain just retrieving enough water for basic needs. A single family requires 20 to 25 liters daily. Acquiring that amount consumes 3 to 4 hours of labor every single day. Education suffers because children spend mornings hauling water instead of attending school. Agriculture remains impossible without irrigation. Healthcare deteriorates because basic sanitation requires water nobody has. Entire communities structured around scarcity rather than development. Then every morning, nature mocks them. Thick Atlantic fog rolls across these same mountains. Moisture surrounds everything. You can feel dampness in the air. Moss grows on rocks, proving water exists. Then within hours, sun burns away all that moisture. It evaporates uselessly while people below desperately need every drop. That contradiction caught German attention. What if that fog could be captured? Germany's Water Foundation studied Morocco's situation and identified an opportunity others had missed. Those morning fog patterns weren't random, they were predictable, consistent, and they carried enormous water content that simply needed harvesting technology. But this wasn't theoretical laboratory work. They needed boots on the ground. Survey teams spent weeks hiking mountain slopes, analyzing microclimates. They measured humidity levels at different elevations. They tracked wind patterns, determining where fog concentration was highest. They examined vegetation, noting that certain plants thrived in areas where fog lingered longest. Moss coverage became a biological indicator of optimal installation sites. Laboratory analysis of captured fog samples revealed something remarkable. The moisture content far exceeded their projections. Each cubic meter of fog passing through these mountains carried enough water vapor that proper collection systems could generate substantial volumes, not just survival amounts, enough to transform how communities functioned. Working with Moroccan partners, they selected installation zones based on multiple criteria: consistent fog patterns throughout the year, elevation providing maximum moisture exposure, terrain stable enough for permanent structures, proximity to villages needing water most desperately. Then came 18 months of relentless testing. Different mesh materials, various grid patterns, multiple collection angles. They needed technology that would survive brutal desert conditions while maximizing water capture efficiency. Extreme heat during day, freezing temperatures at night, violent winds, intense UV radiation. The system had to endure all of it. Finally, they identified their solution, a specialized three-dimensional mesh that would change everything. But getting it installed would push human endurance to its limits. Installation crews faced challenges that made normal construction look easy. Everything required manual transport up mountain slopes where vehicles couldn't reach. Steel frame components weighing hundreds of kilograms, mesh panels in massive rolls, tools and fastening equipment, concrete for foundations, all of it hauled by workers climbing rocky terrain in temperatures exceeding 40 degrees. Local Moroccan laborers familiar with harsh conditions took lead roles. They understood the environment. They knew how to work when heat made every movement exhausting. German engineers supervised technical aspects while local teams handled brutal physical labor. Foundation preparation started with excavation. Crews dug pits approaching 1 meter deep into rocky ground using hand tools because machinery couldn't access these locations. These anchor points would secure steel posts against Atlantic winds that could easily topple improperly installed structures. Each pit placement was calculated, ensuring frames would align with prevailing wind direction for optimal fog capture. Steel frame assembly required coordination that looked like controlled chaos, multiple workers gripping each vertical post as others locked horizontal supports into position. Every joint needed tightening to specifications, ensuring structural integrity. One loose connection could cause catastrophic failure during storms. Workers wearing safety harnesses climbed partially assembled frames, tightening bolts at dangerous heights while wind threatened to knock them off balance. Then came mesh installation, the most delicate phase. These weren't simple nets. They were precision-engineered three-dimensional structures with specific gap patterns optimized for water collection. Stretching them required careful tension adjustment. Too loose, and they'd sag, reducing efficiency. Too tight, and wind forces could tear the material. Workers spent hours on each panel, ensuring uniform tension across the entire surface. But mesh alone wouldn't collect water. They needed integrated drainage systems installed simultaneously. Collection gutters represented critical infrastructure most observers never notice. These V-shaped channels mount beneath mesh panels positioned to catch every droplet sliding downward. Installation demanded precision because gravity does the work only if angles are perfect. Even slight misalignment means water drips past gutters, wasting the entire system's output. Technicians measured multiple times before drilling, mounting holes into steel frames. Each bracket got torqued to exact specifications, preventing movement during operation. Seal integrity between gutter segments was verified obsessively because leaks would compromise everything. These channels would funnel collected water into primary pipes, traveling potentially kilometers to storage facilities. The complete CloudFisher system operates on principles of elegant simplicity. No motors, no pumps, no electrical systems, just physics. Fog flows through mesh. Moisture condenses on cool surfaces. Gravity pulls droplets downward. Collection systems channel water to storage. The entire operation requires zero energy input beyond what nature provides through wind and temperature differentials. This simplicity makes the technology revolutionary for remote regions. No fuel costs, no maintenance requiring specialized technicians, no complex machinery that breaks down. Just durable materials configured correctly continuing to function year after year. Perfect for aid organizations working in areas lacking infrastructure or technical support. From distance, completed installations look almost artistic. White mesh panels catching light like sails against brown mountain slopes. But they're not art. They're survival infrastructure, and they work through mechanisms most people never consider. The physics behind CloudFisher technology operates at microscopic scale. Fog isn't empty air. It's atmosphere saturated with tiny suspended water droplets measuring micrometers in diameter. Individually, they're nearly invisible. Collectively, they form the white mist obscuring visibility. When wind drives this moisture-laden air through mesh barriers, something remarkable happens. Those microscopic droplets collide with polyethylene fibers. The cool surface triggers condensation. Individual droplets merge, forming larger accumulations. Surface tension holds them temporarily before gravity overcomes adhesion. They slide downward, following mesh angle into collection gutters below. The double-layer mesh design maximizes capture efficiency. First layer catches initial droplets. Second layer captures moisture passing through, creating redundancy that dramatically increases total water harvest. The three-dimensional structure provides massive surface area within compact space. Millions of individual contact points where condensation occurs simultaneously. During optimal conditions, when dense fog persists for hours, you can actually watch water streaming into gutters. Clear liquid flowing from air that appears empty to human eyes. The visual disconnect is striking. No visible source, just moisture materializing as if by magic. But it's pure engineering exploiting natural processes. Production rates vary based on fog density and duration. Average systems with 10 panels generate between 600 and 1,000 liters daily. During peak fog season, that number increases substantially. Even during dry periods when conventional wisdom says no water exists, CloudFisher units continue producing because atmospheric moisture remains even when visible fog disappears. For communities accustomed to water scarcity, these volumes represent transformation, but distribution created unexpected social challenges. Village residents initially assumed fog water would be free. After all, it comes from air. Nobody owns the fog. German teams quickly realized that approach would guarantee failure. Free resources get wasted. People leave taps running. They use water carelessly because abundance feels unlimited. Within weeks, storage tanks would empty and the system would fail, serving anyone. Instead, they implemented a usage-based pricing model. Residents pay for water consumed, measured through individual meters. Rates average $1.2 to $1.5 per cubic meter. Not expensive by developed world standards, but significant for rural Moroccan households earning minimal income. The economic model serves multiple purposes. It prevents waste through financial incentive to conserve. It generates revenue funding system maintenance and expansion. It creates local employment for meter readers and maintenance workers. Most importantly, it establishes water as a valuable resource requiring responsible stewardship, rather than something taken for granted. But this pricing structure created uncomfortable inequities. Families with any income can afford regular access. They turn taps and water flows for cooking, cleaning, bathing. Children attend school instead of hauling water. Women pursue income-generating activities instead of spending hours on water collection. Meanwhile, the poorest families still can't afford even these modest rates. They continue walking multiple kilometers to contaminated sources. They scoop water from hand-dug pits, knowing it carries disease. They carry 20-kilogram loads on their backs in brutal heat because they have no alternative. The technology solved problems for many, but poverty remained an insurmountable barrier for others. Despite these complications, the numbers tell remarkable stories. Between spring of 2016 and late 2018, installation crews completed what became the world's largest fog harvesting operation. Over 1,600 square meters of active collection mesh now operates across Morocco's Anti-Atlas region. The infrastructure serves 15 separate villages totaling 1,250 residents, plus educational facilities requiring clean water. Agricultural applications expanded possibilities beyond human consumption. 7,000 livestock now have reliable water access, enabling herding activities that were previously unsustainable. Crop irrigation allows food production in areas where farming had been abandoned. Economic opportunities emerged as communities gained time previously consumed by water acquisition. The physical infrastructure is impressive by any measure. 31 separate CloudFisher installations connected through 26 kilometers of pipeline network. 5 storage facilities with combined capacity approaching 1,000 cubic meters. Every square meter of mesh produces roughly 22 liters annually. Total system output exceeds 36,000 liters daily, translating to over 13 million liters annually. Maintenance requirements remain minimal. Occasional mesh cleaning, periodic gutter inspection, structural integrity checks after major storms. But no fuel costs, no electricity bills, no complex mechanical systems requiring specialized repair. The installation represents essentially a one-time capital investment, generating returns indefinitely with minimal ongoing expense. Environmental impact approaches zero. No groundwater depletion, no ecosystem disruption, no pollution or waste products. Just passive collection of moisture that would otherwise evaporate unused. The technology works with natural processes rather than against them. German engineers proved something remarkable. Water scarcity isn't always about lack of water. Sometimes it's about lack of technology capturing water that exists but remains inaccessible. But while Germans harvest fog, another nation is attempting something that seems even more impossible. Northern China faces an enemy that has threatened civilization for centuries, advancing deserts consuming productive land. Each year, massive dust storms originating in the Gobi and Taklamakan deserts blanket Beijing and other major cities. Residents experience days where breathing outdoor air feels like inhaling sandpaper. Visibility drops to meters. Respiratory illness spikes. Economic activity grinds to halt. By the 1990s, the situation approached crisis levels. Citizens wore protective masks over 80 days annually just functioning outside. Deforestation and overgrazing accelerated desertification, spreading across northern territories. Vegetation disappeared, soil quality collapsed, groundwater tables dropped from excessive pumping. The desert was winning. China's response was characteristically audacious. In 1978, they launched the 3 North Shelter Belt program, known internationally as the Green Great Wall. Not a single barrier, but an interconnected network of forests, windbreaks, and ecological restoration zones extending over 4,500 kilometers, from Xinjiang in the west clear across to Heilongjiang in the east, covering nearly the entire northern frontier. The goal defies easy comprehension: plant 35 million hectares of new forest by 2050, increase national forest coverage from 10% to over 25%. Transform desert and degraded land into productive green zones. It represents the largest ecological restoration project ever attempted anywhere on Earth. Not built with concrete or steel, built with trees. Billions of them. But you can't just plant trees in desert and expect them to survive. China needed technology nobody had developed before. Chinese engineers studying the Taklamakan confronted immediate challenges. How do you stabilize sand that shifts constantly with every wind? Traditional approaches failed immediately. Plant directly in sand and seedlings either get buried by migrating dunes or their roots remain exposed as substrate erodes away. Success required controlling sand movement first. Then planting could proceed. The solution came from agricultural waste. Straw checkerboard barriers installed in massive grid patterns across dune surfaces. Each square measures roughly 6 meters per side. From ground level, they look like simple trenches with straw bundles. From aerial views, they transform landscape into enormous golden checkerboards extending toward horizons. But creating these grids demands brutal labor. Millions of kilograms of straw transported hundreds of kilometers into desert interior where roads don't exist. Vehicles sink in loose sand. Equipment fails in extreme heat. Workers dig shallow trenches under conditions where temperatures exceed 49 degrees with zero shade available anywhere. Every movement becomes exhausting when heat radiates from ground and sky simultaneously. Thousands of laborers persist despite conditions because each grid square serves critical functions. The barriers slow wind velocity dramatically. Airflow carries less sand. Dune migration rates drop. Microclimate zones form within protected squares where moisture can actually accumulate instead of evaporating instantly. These become planting locations where seedlings have survival chances. Over time, the straw decomposes, enriching soil with organic matter in substrate that previously contained nothing but sterile sand. Microorganisms establish. Soil structure begins developing. Moisture retention improves. The transformation from pure sand to something approaching actual soil takes years, but the process starts with those simple straw barriers. Once grids establish microclimate protection, planting machinery moves in, but species selection determines ultimate success or failure. Not every tree survives desert conditions. Species selection required extensive research identifying plants with extreme drought tolerance, temperature resilience, and root structures capable of stabilizing sand. Saxaul, desert poplar, red willow. Native species evolved for these brutal environments where annual rainfall barely reaches 100 millimeters. Nursery operations cultivate seedlings under controlled conditions, ensuring robust root development before desert exposure. Each young plant gets hardened, gradually preparing for transplant shock. When ready, they travel to installation sites in protected containers, minimizing stress during transport. Planting crews work with precision. Mechanical augers drill holes at grid square centers, reaching depths where some moisture remains. Seedlings position carefully, ensuring roots extend into substrate that won't dry completely. Workers add measured water amounts, providing initial hydration. Soil gets compacted around stems, creating contact between roots and surrounding material. Every step follows protocols developed through years of trial and failure. The straw grid continues serving protection functions during early growth. Shading reduces surface temperatures around seedlings. Wind protection prevents desiccation. The decomposing organic matter feeds developing root systems as they extend deeper, seeking stable moisture layers beneath surface sand. Initial survival rates remain modest. Many seedlings fail despite best efforts, but enough survive that over years, living vegetation networks establish. Roots anchor dunes, preventing migration. Plant transpiration adds moisture to local atmosphere. Organic matter accumulates as plants grow and shed material. Slowly, ecosystem functions emerge where only sterile desert existed before. The transformation happens slowly, but undeniably. Satellite imagery captures the change dramatically. Where brown dominated every image, green now spreads across landscapes. The desert hasn't disappeared, but its advance has stopped. And in places, it's actually retreating. Something nobody thought possible. You've witnessed how German engineers deploy mesh technology, pulling 36,000 liters daily from Moroccan fog at 2,000-meter altitudes, transforming water scarcity for over 1,200 residents. And how China fights desertification across 4,500 kilometers using straw grids, stabilizing sand before planting billions of trees in the largest ecological restoration ever attempted. From CloudFisher systems operating on pure physics requiring zero energy to the Green Great Wall, representing determination measured in decades and millions of hectares, technology is proving that Earth's harshest environments aren't permanent. They're challenges waiting for solutions. What fascinated you most? The fog harvest simplicity? The straw grid innovation? The sheer scale of ambition? Drop your thoughts below. Thanks for watching MacroForge, where we explore engineering that refuses to accept impossible. See you in the next one.